Today we're talking about graphing rational functions, and as you know, rational functions are functions that can be written in the form of a fraction. And so just like when we were reducing rational expressions, we want to always factor first and see if we can do any reducing. So in the process of graphing these functions, we're going to look for x-intercepts. X-intercepts are the points where the graph crosses the x-axis. In other words, y is equal to 0. Function, when we talk about the function, we're talking about the y. So we set the function equal to 0 and solve to find the x-intercepts. Y-intercepts are the points where the graph crosses the y-axis. And so in that case, our x is 0. So we plug zeros in for all the x's and simplify, and that will get you the y-intercept. We look for any vertical asymptotes that may occur, the value which would be at the values of x that make the denominator equal to 0 and are non-removable. In other words, once you factor and you cancel any of the factors that are left in the denominator, when you set those equal to 0, that would tell you where there's a vertical asymptote. So factors that cancel do not cause vertical asymptotes. Factors that cancel cause holes. The factors that remain in the denominator, set them equal to 0, and that's where your vertical asymptotes are located. Horizontal asymptotes, when you're looking for those, you're looking for the values of the function as x approaches positive and negative infinity. In other words, if you've got a graph that looks like this, then we've got a vertical asymptote here, and when you sketch your graph, and let's add a horizontal asymptote too, and have a horizontal asymptote here. When you sketch your graph, as the graph is approaching positive infinity or approaching negative infinity, it does so at the location where the horizontal asymptote is located. Okay, so let's look at the different ways we can find the actual value of that horizontal asymptote. Okay, horizontal asymptotes. There's three different cases when we're dealing with horizontal asymptotes. First case is when the degree in the numerator is less than the degree in the denominator. In that case, the horizontal asymptote is equal to y equals 0. So, for instance, if I've got f of x is equal to x plus 2 over x squared minus 5x plus 3. When the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0, the x-axis. Case 2, second scenario, is when the degree in the numerator is equal to the degree in the denominator. In that case, the horizontal asymptote is the ratio of the coefficients of the terms with the largest degree. For instance, f of x is equal to x squared plus 2x plus 3 over 2x squared minus 2x minus 3. So note, the degrees are the same. The largest degree of all of the terms is the same on top and bottom, numerator and denominator. So what we do is we look at the coefficients of these terms, and we set that value equal to y, and that would be the equation of the horizontal asymptote in that case. The third case is when the degree in the numerator is greater than the degree in the denominator. In that case, there is no horizontal asymptote, none at all. So, for instance, f of x is equal to x cubed over x squared plus 1. In that case, there is no horizontal asymptote. However, in the next lesson, we'll talk about a different type of asymptote that would occur in that situation. Okay, but for now, just no horizontal asymptote. All right, then we briefly talked about wholes a minute ago. I said any of the factors that cancel in the numerator and denominator would give you a value that's a whole. And so as you're graphing these functions, if you've got a whole, you need to make sure that you put a big open dot on top of the line wherever that whole would occur. And once again, those holes show up when you have a factor that cancels in the numerator and denominator. So in this case, these factors would cancel, so set that equal to 0, and that tells you where your whole is located. Okay, so that's everything we need to know to get started. Look at the first example. For each of these examples, we want to identify all the x and y intercepts. We want to identify the horizontal and vertical asymptotes. We want to identify any points of discontinuity, which in this case is going to be holes. We want to sketch the graph, and then finally we want to state the domain and the range. Okay. Okay. For this first example, we've got f of x is equal to 4 divided by x minus 5. So our first step is always to factor and see if there's anything that will cancel, but there's nothing here that would be able to be factored or canceled. So since there's no factors that cancel, we have no holes. Now we want to talk about the asymptotes. Let's start with the vertical asymptote. Remember, vertical asymptotes come from factors in the denominator set equal to 0, the factors that did not cancel. So we have a vertical asymptote at x equals 5. So I'm going to come over here where x is equal to 5. I'm going to sketch a dotted vertical line for the vertical asymptote. What about horizontal asymptotes? In this case, the horizontal asymptote, if you look at the degrees, the degree in the numerator is 0, the degree in the denominator is 1. So if the numerator degree is less than the denominator degree, our horizontal asymptote occurs at y equals 0. Okay, so let's sketch in the horizontal asymptote. Y equals 0. Okay, now let's go to x-intercepts. X-intercepts are the point on the graph that cross the x-axis where y would be equal to 0. So if I take this function, f of x, and set the y equal to 0, and then solve, you'll see that there is no, if I cross multiply here, x minus 5 times 0 is 0 equals 4, there is no value of x that would cause that to be equal to 0. So there are no x-intercepts. And that makes sense because that horizontal asymptote is where the x-intercept would occur. However, if you remember, our graph can cross a horizontal asymptote. It just can't cross a vertical asymptote. Okay, y-intercepts, that's where x is equal to 0. So if I set the x is equal to 0 and solve for y, I get y is equal to negative 4/5. So the y-intercept when x is 0, y is negative 4/5. So I'm going to come over to my graph and find the point 0, negative 4/5, and put my point on there on the y-axis. And now I have to figure out, based on one point and two asymptotes, how to sketch my graph. And so when you're sketching these graphs and you've got vertical asymptotes, You know that there has to be something happening on either side of those vertical asymptotes. So you need points on either side that you can test to find out what's going on. And so we need to choose just a few more points. One point's not going to tell us everything. So let's start out with the left side, to the left of the vertical asymptote. I have this one point. I'm going to choose another point to test. So if I were to choose, say, x is equal to 3, that would be right along in here. And so if I plug a 3 in for x, I get 4 over 3 minus 5, or 4 over negative 2, and I get negative 2. So there's a point at 3, negative 2. Now based on those 2 points and based on the 2 asymptotes, I could pretty well make the assumption that my graph is going to curve like that, because it has to curve towards those asymptotes. It has to be approaching, getting very, very close to the asymptotes. What I don't know is anything about what's happening over here to the right side of that vertical asymptote. So I'm going to need a couple points over there, because my graph could appear above that horizontal, or the graph could appear below the horizontal. I don't really know where it is yet, so I need to test a point over there. So I'm going to test the point 6 for x. And when I plug a 6 in, I get 4 over 6 minus 5, or 4. So I know that there's a point at 6, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 6, 4. If I were to plug in another point, maybe 8, I'm pretty sure I know what it's going to do, but I'm going to test it just to make sure. So 4 over 8 minus 5, or 4/3. So at 8, I'm at 4/3. And so now, based on those 2 points and based on those asymptotes that I know I have to approach, I can sketch the rest of the curve. So that's what the graph is going to look like. We still need to list our domain and range. So the domain is all the x values. So starting at the far left, I would start with negative infinity. Go up to where your vertical asymptote is. Vertical asymptote is at 5. So negative infinity to 5, I don't include the vertical asymptote. And then I need to union that with the second set, which would start at 5 again and go to positive infinity. For the range, those are the y values. I'm starting at the lowest value again and working my way up. So start at negative infinity, and I'm going up to the horizontal asymptote, which is at 0. And then make sure that you don't include that. Union it with the top part, so 0 to positive infinity. And that's everything that you need for that particular graph. Okay, example number 2, same process. This time, however, our function can be factored, and then we can look and see if we can reduce it. So factoring, the numerator's okay like it is, but the denominator will factor into an x minus 1 times an x plus 4. So at this point, notice you've got an x minus 1 in the numerator, you've got an x minus 1 in the denominator. So those factors are going to cancel, which is what's going to give you your whole. And so x minus 1 equals 0. There's a whole at x is equal to 1. In order to find the y coordinate that goes with that x coordinate for the whole, I have to plug that x value back into the reduced version. Okay, so the reduced version of my function now is f of x is equal to 1 over x plus 4. I have to plug this one back into the reduced version, because if I plug it back into the original, I'm just going to end up with a 0 over 0, which doesn't help me any. And so plugging a 1 in, f at 1 is equal to 1 over 1 plus 4, or 1/5. So my y coordinate then for the whole is 1/5. So at 1, 1/5, I have an open hole. I'll go ahead and put it on there so I don't accidentally forget it later. Okay, at this point we can work strictly off of the reduced version of our function. You do not have to go back to your original version. You can use the reduced version. So finding asymptotes. Start with the vertical asymptote. Vertical asymptotes come from factors in the denominator that didn't cancel. In this case, the x plus 4. So x plus 4 equals 0. X equals negative 4 is my vertical asymptote. So vertical asymptote at negative 4. Horizontal asymptote. Remember, we're looking at the degrees of the numerator and the denominator. The degree in the numerator is 0, denominator is 1, so that's another y equals 0 situation. So y equals 0. Okay, x-intercepts, that's where y is equal to 0. So if I take my reduced function and say 0 is equal to 1 over x plus 4, you can see once again that there is no value that x could take on that would make that equal, that 1 plus 1 over x plus 4 equal to 0. So there are no x-intercepts again. Y-intercepts, that's where we plug in a 0 for all the x's. So y is equal to 1 over 0 plus 4, or 1/4. So the y-intercept is at 0, 1/4. So come over here and put a point, 0, 1/4. All right, now we need points again. We've got a hole and we've got 1 point to the right of the vertical asymptote. So let's get one more point to the right of the vertical asymptote. So if I picked maybe a negative 2 for my x, then y is equal to 1 over negative 2 plus 4, or negative 1/2. So negative 2, that's wrong, positive 1/2, my bad, positive 1/2, so negative 2, positive 1/2. If I pick a negative 3 just to make sure, because I'm wanting to make sure that it's really heading up along that vertical asymptote, y is equal to 1 over negative 3 plus 4, or 1. So negative 3, 1. So it's gradually coming up along here. Make sure you don't draw through that hole that you sketched. And now we don't know anything about to the left of the vertical asymptote, so I need several points to the left of the vertical asymptote. So I'm going to try a negative 5. And so when I plug with negative 5 in, y is equal to 1 over negative 5 plus 4, I get negative 1. So negative 5, negative 1. Now, because we know how these asymptotes work, and we know that the graph has to be approaching them, just knowing that I'm below this horizontal asymptote tells me that my lines are going to have to be approaching the asymptotes in that manner. What I was doing when I was testing this negative 5 was trying to decide, am I below the horizontal asymptote or am I above it? Because my graph could have occurred in either of those locations. All right, so now I can do my domain and range. So starting with the smallest x, negative infinity, up to the vertical asymptote, which is negative 4. Union that with the next section, so starting at negative 4, notice I'm not including those points. And now be very careful with the next one. You want to go up to the hole, but not include the hole, and then from the hole again to infinity. For the range, those are the y values, starting with the smallest again, negative infinity, going up to that horizontal asymptote, that's 0. Union that with the next section, 0, 2, and be careful here because there's another point missing where that hole is. There's another y value missing. And so from 0 to 1/5, not including the 1/5, and then union that with 1/5 to infinity. All right, our last example. We want to start by factoring again. So f of x is equal to -1 over, and the denominator is going to factor into x minus 6, x plus 2. There's nothing that's going to cancel, which tells us there are no wholes. Asymptotes, now for vertical asymptotes, notice that we have two factors in the denominator that didn't cancel. Both of those factors are going to create vertical asymptotes. So x minus 6 equals 0, so x is equal to 6. And x plus 2 equals 0, so x is negative 2. So two vertical asymptotes, one at negative 2 and one at 6. Okay, our x-intercepts once again, that's where y is 0, and so there's nothing that you could plug in for x that would make that fraction equal to 0, so no x-intercepts again. Y-intercepts is what we get when we plug 0 in for the x's, so y is equal to -1 over 0 squared minus 4 times 0 minus 12, which is -1 over -12, or 1/12. So we've got a point at 0, 1/12. So y-intercept is at 0, 1/12. Really, really close there. Let's back up a minute. We forgot to do the horizontal asymptotes. Let's go back to the horizontal asymptotes and look at the degree of the numerator, which is 0. The degree of the denominator is 2. So that gives us another horizontal asymptote at y equals 0. Okay. Alright, so now we're ready to find some points. We have one lonely little point on our graph. We need more points. We've got this one point, the y-intercept, that's in between these two vertical asymptotes. I need a lot of information to talk about what's happening in between those vertical asymptotes, because there's three different things that can happen. I could have, because this point is up here, I could have a graph that does this. Okay. Or sometimes when you've got two vertical asymptotes, your graph will come along and then go through the vertical asymptote all the way to the other side. And so I need to know whether it's coming down to that point and curving back up, or whether it is going through the horizontal asymptote all the way to the other vertical asymptote. So I need to pick some points to test. So I've got a point where x is 0. I know that it's going to have to head up this direction. What I don't know is what happens as I'm heading to the right. So I'm going to pick another couple points. So maybe where x is equal to 2. And when I plug 2 in to that function, -1 over 2 squared minus 4 times 2 minus 12, I get -1 over -4, -16, so 1/16. So at 2, I'm still positive. I'm at 1/16. It's very, very close, but I'm still positive. So now I'm going to test at 3. Actually, let's go 1, 2, 3. Let's go to number 4, where x is 4. Because at that point, if it's going to head up, it will have stayed up. If it's going down, it would have gone negative. So when I plug a 4 in then, I have -1 over 4 squared minus 4 times 4 minus 12. And look, this is going to be the same thing. 16 minus 16, and then minus 12, so I've still got 1/12, so I've got the same, well, close, 1/12, not 1/16, but it's still positive. So at 4, I'm still positive, so that's enough to tell me that I'm going to be heading back up again, not down through. All right, now I need points on the outsides. So to the left of the first vertical asymptote, if I pick a -3, and plug it in, I'm going to get a negative 1/9. So negative 3, negative 1/9. That tells me I'm going below. So I'm going to sketch that curve like that. Then I need to pick one on the right hand side, so I'm going to pick a 7. And when I plug a 7 in, I get negative 1/9 again. So at 7 it's negative 1/9. So now I've got a curve that looks like that. So, moral of the story, when you've got vertical asymptotes, you need to test x's in every section that's divided by those vertical asymptotes. So in this case, there were 3 sections. There was to the left, there was in the middle, and there's to the right. You need points in all 3 of those sections. And especially in the middle section, you need to be especially careful because that graph can cross that horizontal asymptote, and sometimes it does. So watch out for that. All right, so now let's talk about the domain. Starting at the left with negative infinity, going up to that vertical asymptote at negative 2. Union that with the next section, which is negative 2 to 6. And then union that with 6 to infinity. The range now, we're starting down here at negative infinity, and these outside edges are going up very, very close to that horizontal asymptote, approaching it, and so we go to 0. The middle section, however, is a separate situation. This middle part does not go infinitely close to that horizontal asymptote. It kind of stops right about that point right there. And so when we tested that point, we got a negative 1/16. So the y value here is negative 1/16. There's a slight little bit of section here that's not represented in our range. So I want to start then the second section, include that point, negative 1/16, and then go to infinity. Be very careful finding your range when you've got one of these middle sections, because you need to know where that y value is in the center. Sometimes it will be the exact center point. Sometimes it won't be the exact center point. Sometimes you'll have graphs that do kind of weird things, and so you're going to have to test a bunch of points to make sure you're getting the one that's the closest to that horizontal asymptote for your range. Okay, so that is graphing rational expressions.